Okay, so we have seen that the Fourier transform is quite a powerful tool. It helps us to understand invertibility and even compute the spectrum of convolution operators, which are pretty arbitrary bi-infinite matrices with constant diagonals. In fact, you can do even more with, let's call it the big brother of the Fourier transform. Suppose you have a bi-infinite matrix with only finitely many non-zero diagonals. It's a band matrix. But this time the diagonals, let's for simplicity say just 3 of them, the red, the blue and the green diagonal, are not constant, but they are periodic. So along the blue diagonal you see certain numbers, and then after a certain period same numbers occur again, and then again and again, and so on. Okay, the same happens on the red and on the green diagonal. The periods, the red and the green and the blue period, could be different from each other, but if you have 3 numbers, then you could take the smallest common multiple of these, and then that's again a period for both red, blue and green. So let's for simplicity assume we already have that smallest common multiple, and then they are all 3 periodic with the same period. And then someone asks you things like invertibility or even the spectrum of A. How do you do that? The idea is to cut your bi-infinite matrix A in blocks, where the block size is equal to that period. So if you call the period little p, then these will all be p by p submatrices. And now on this block level, let's look a bit closer maybe. A has again constant diagonals. If we denote that first block by A0, then we have A0 again here and here and so on, and then let's call that one A1, and this is then here and so on, and this is A minus 1, and you can again see it here. And maybe there is even a little bit of A2 here, and that would be A minus 2, and then the story goes on as a block Laurent matrix or operator. And the Fourier transform idea can also be extended to these operators. And essentially what you have to do is, well, you understand this again as an operator on little L2 over the integers set. But just like you were splitting your matrix in blocks of the size p by p, you're now splitting your vectors in, well, subvectors of length p here and here. And then you rearrange your space L2 set so that you do not only understand it as scalar valued sequence, but you could also understand it as sequences of infinitely many vectors of length p, one sitting on top of the other, and each one of these vectors is just equipped with the 2 norm, and then you take the Euclidean norm of this infinite vector of vectors, and again in the end you're back to L2 of set. So what you have to do is now identify these vector valued L2 spaces with capital L2 spaces over the unit circle, and they will also be vector valued with vectors of this size. And then it turns out that convolution on this vector valued little L2 corresponds, after a certain Fourier transform, to multiplication by a matrix, and that's a p by p matrix valued function. And let's denote that function again by a upside down hat. And the construction is just the same. You have t running through the unit circle, and then the block entry on the main diagonal, which is now capital A0, is multiplied by t to the power 0, and capital A1 multiplied by t to the power 1, and so on. Now that is obviously a matrix valued function, and invertibility and spectrum of A are characterized as follows. So your A is invertible if and only if that matrix valued function here is always invertible, no matter what input on the unit circle you take. So in the scalar valued case, that used to say has no zeros, because 0 is the only non-invertible scalar number. But now you have to avoid the non-invertible matrices. Okay, and what's the spectrum? Well, the spectrum of A is now the set of all complex numbers lambda for which, similarly to before, there exists a point t on the unit circle such that the corresponding, now this is a matrix here, if you subtract lambda times the little p by p unit matrix, is not invertible. This used to say equals 0 here when we derived the formula for the spectrum. That was here. Okay, but now I think we can simplify that. And this is just the union of all spectra of these matrices A upside down ahead of T, where T is running through all points of the unit circle. Because that here just means lambda is in the spectrum of this guy, and the fact that there exists one means you have to take the union.